All right, as y'all find your seats, the Slido is active. There's some stuff to discuss on the board. Chat through. Select which of these is false. That's the question for the day, and we'll come back in like 4 minutes. Go ahead, chat. All right, let's see what we have selected. Let's show these results. I see 108 of you have responded. Oop, okay, 110. Love it. All right, let's see. Oh, interesting. Okay, let's talk through them sort of bit by bit. Okay, a piece of code whose model is f of n equals 3n plus 6 has a simplified tight big O of O of 2n, I think is what that was supposed to look like. Did it look like 2n on yours? Did it look like n squared? Did it look like n squared? Okay. Let's call it n squared. I think it misinterpreted the characters. So let's say it's n squared. I am going to agree with 96% of you. This is false. Now, is O of n squared a correct big O? Notice how I did not say simplified or tight. Is O of n squared a big O of this function? Yes. Is O of n squared a simplified big O? Yes, it is a simplified big O because I don't have any of the extra coefficients or any of the extra constants. But the question is it a simplified tight big O? No, it's not tight. So the tight big O of this function would be O of n, not O of n squared. It is still upper bounded by n squared, so it's technically a correct big O, but it's not the tight big O. That's the difference in that definition. And something to keep in mind that when people ask for big O, they probably mean tight big O if you're, say, in an interview. And I will be very specific on any exam and will tell you the simplified tight if that's what I'm looking for. Any questions on that one? Cool. I want to make sure we're clear on that definition. Okay, let's look at the second one down. The tight upper and lower bound of a piece of code's runtime growth is always the same complexity class. On Wednesday, we saw some examples. Did we see any examples on Wednesday for which this was not true? Does anyone remember? Yes, in the back. Yes, so that is a situation where that one's tight upper and tight lower, if the function's just log n, would be log n. But you're right, it would be upper bounded by n. It wouldn't be lower bounded by n, though, in that particular case. But if you remember that piece of code that we were working on and then I fixed it, it's the return false and return true were flipped on that one. The is prime number, do you remember how it had an upper bound that looked kind of linear and then a lower bound that looked constant? So that is an example of a piece of code where the tight upper and lower bounds are not the same complexity class. So this is false. And then that rolls us into the next one down. The big theta will exist for every function. I am also going to agree with the 87% of you that is also false. The is prime is an example of a function where the theta does not exist because its tight upper bound and tight lower bound are different complexity classes. That's the scenario where the theta doesn't exist. If the tights are the same, if there's like that nice kind of fit, then the theta exists. But the thing that's annoying is I'm using this word fit, and I know there's a mathematical definition of that word where like it would maybe try to find an average in the middle. That doesn't exist in this context. For the theta to exist, the tight upper bound and the tight lower bound have to be the same complexity class. And then finally, if a function is in O of n squared it cannot also be omega of n squared. I also agree with the 78% of you that this is also false. These were all false. That was my little trick there. And that is, there is one particular complexity class for which it is both big O of n squared and omega of n squared. Does anybody know that complexity class? The tight upper limit is n squared. The tight lower limit is n squared. So what do we think that function's complexity class is? N squared? Yeah, yes. Yeah, I wasn't trying to trick you. Yes, absolutely. So again, we remember in the definitions, it's like big O, the function has to be less than or equal. The omega, it has to be greater than or equal. And those equal signs make it so this situation, a function whose complexity class is n squared has a tight big O of n squared, an omega, a tight omega of n squared, and thus its theta is what? Anybody? Bueller? If its big O is n squared, tight big O is n squared, and its omega is n squared, what is its theta? Yeah, yay, okay, n squared. Does anyone have any questions about the definitions of big O, big omega, or big theta at this time? Well, if you do and you don't want to say them aloud here in this intimidating room, please feel free to use the Q&A section of the Slido. The TAs will be happy to answer your questions, and I'll pop it up when we get to the questions later on in the lecture. But thank you all for indulging me with our warm-up. That's not the warm-up or the slides. This is what I'm looking for. There we go. Okay, so let's talk today. The announcements, no new announcements. Project 1, DEX is out. It will be due next Wednesday. Exercise 1 is also out. It will be due on Monday. After today, you'll have everything you need to answer all of the questions on the exercise, and it'll be due at 11:59 on Monday evening. Does anyone have any course administrative questions at this time? Okay, cool. Also, you could have had partners on P0, but a lot of people like to do the setup themselves. I find that most times people start to really find partners for P1, and so this is my reminder to you as your buddy who wants you to do well in this course. Find project partners. Shout out to whoever made the Discord. I am not on the Discord, nor are the TAs. That is for you to talk. I have no responsibility of what goes on in the Discord. But also maybe go there to find some project partners, or maybe go to section and meet people in your section. Also, I will just say it, we don't have anyone in this class after lecture, so if you are looking for a project partner, hang out, let's say over there, and you can have yourselves a little project partner, let's call it mixer, yeah? Find partners. It will make your life easier. You are more likely to be successful in this course. I strongly encourage you. But you're adults, so do whatever you want. Okay, great. So let's talk about some stuff. So we were supposed to get to this topic on Wednesday, and I totally didn't have time. So we're going to try and talk about this topic and the recursion stuff. We'll see how far we get. So if you remember this sort of design, we are working our way through the roadmap of how to analyze code. We started with code model. So we went from the actual code you write to this sort of mathematical model that relates the size of the input to how many instructions are going to be run. That's that code model section. Then we went on to asymptotic analysis. We met big O, we met big omega, we met big theta. Well, let's add another layer. So we're going to start here with an example. Let's say we are writing the code for linear search. Linear search is the algorithm where, let's say I have an array list of a bunch of values, and I asked you to find a specific value. Let's say I asked you to find the value 2. Well, what I would do is I would start at index 0, and I would say, hey, are you the value I'm looking for? Well, gosh darn it, isn't it so convenient that the very first thing that exists in this collection happens to be the thing I'm looking for? It's almost as if this could have been a collection of thousands of items, and I don't even care because I'm going to find the thing I'm looking for right away. That's really convenient. You could say that's almost like the best possible outcome. It's like the best case scenario. Flip side. Let's say I asked you to look at the same collection, same number of inputs, same overall size, but now I'm asking you to find the value 8. Well, the way that you would do it is you would start at index 0 and you'd be like, hey, are you 8? Nope. So I guess I go next door. Are you 8? Nope. Okay. I go all the way through. In fact, I have to look all the way through to the very end of the list to determine that 8 is not in it. So that's kind of the bummer. That's like the opposite side of that. It's sort of like, oh gosh, that's the worst case scenario. Welcome to case analysis. So there are also ways for us to think about how our code is going to behave based on the state of the data, not the size of the data, the state of the data. So our best case scenario in linear search is that the thing I'm looking for is in the list and it happens to be at index 0. I don't care how big the list is. That's going to run in constant time, whether there's 10 items in that list or 1,000 items in that list or 1,000,000 items in that list. So we get that nice little like f of n equals 2. In our best case scenario, maybe that 2 is like, hey, is this the thing I'm looking for? Return yes, something like that. But again, the worst case scenario is the thing I'm looking for doesn't exist in the list, and I've got to check every single place in the list before I can determine that the thing's not there. And in that situation, it does matter how many things are in it. If there's 10 things to determine, like to look at before I determine it's not there, it's a very different situation than if there's 10,000. So then my worst case scenario, maybe it has like a 3n plus 1, because maybe there's like 3 things I do inside of a for loop that has to run n times to look at everything, and then there's like a plus 1 return false or something at the end. So in this situation, the best case versus the worst case actually has a pretty significant difference in how that code is going to behave. This is called case analysis. You will find in general we are pessimists in this particular subject space. And so often people are asking you to look at the worst case, but that doesn't always give us sort of like the most holistic picture of our code. And so now this is the time where we're asking you to start thinking about like what is the possible state of that code that could trigger some of the most tedious or some of the most slow or some of the most inefficient code to run, or on the flip side, like what is the ideal situation so I could quickly get the answer that I'm looking for. Technically, every sort of different value in between the best and the worst, you could argue that that's its own case. Like what if the thing was in the middle? Then it kind of runs in half of n. It's still the same complexity class, but it's a little different. But we usually don't look at those intermediary cases. We kind of always ask about the extremes, and that gives us this sort of range of how that code may behave. So the best case scenario, what's the absolute fastest our code could run regardless of the size of n? Remember, in the linear search, it doesn't matter if the n is 10 or the n is 10,000. Same thing with worst case. What's the absolute slowest our code could run regardless of n? Here are some more examples. This is a really sticky spot. I find that students tend to mix up these two things very commonly, where I will ask them, what's the best case scenario? And they will often try to tell me a size of input, like, well, the best case scenario for linear search is when there's only one thing to look at. And the worst case is when there's like infinity things to look at. That's technically true in English language form, but that's not case analysis because I can't really make design decisions based on that, That's not going to help me in this particular style of analysis. Other really common misunderstandings of this are like, oh, well, what if front's pointing to null? That's a really effective and efficient way to tell, like, hey, there's no duplicates, or hey, there's nothing in it. Nope, we can't vary the number of n. Same thing with like overall root points to null, or best case when n is like an even number in the is prime. Also doesn't work because we need to always do our case analysis as n tends towards infinity. It's not about the count of n, it's about the values or the state of the data structure. So correct case analysis would be like when the node I'm looking for is at the very front of the linked list, and that's where I start. Worst case is when it's like not in the list, I gotta look at everything. Or if you remember sort of like binary search trees, if a binary search tree is perfectly balanced, like all of the sort of branches are full so that every time I go left or right, I'm sort of eliminating half of the possible choices, that's the best case scenario. If the binary search tree is what we would call degenerately formed, that's not my term. Feels very judgmental. But if it's just like one long linked list to the right or something like that, it's like if I try to go left or right, I'm not eliminating half the choices anymore. So that's like the worst case scenario. I can still have a tree with the same number of nodes. I could have a tree with 10 nodes, 1,000 nodes, but it's about the structure of how those nodes are organized that will indicate the best or worst case scenario. Questions? Questions about case analysis? I feel like it's one of those things where I say it and everyone's like, yeah, totally. And then I'm like, okay, given this scenario, what's the best case? And then somebody will be like, when the front is null. And I'm like, so close, my love. I swear this confuses everybody. We'll get there, okay? Great. Here's some other cases. These are things I'm not really going to talk about for the rest of the class, but hopefully at this point you're like, wow, Casey, there's a lot of ways to think about my code beyond just does it work or not. So here's some other things to think about. We'll talk about code in like, oh, assume this unfortunate thing doesn't happen. Like you'll see situations where like people want to talk about the code, but like assume the resizing of the array doesn't happen. That's a really common thing that people will say. Or if you want to continue on and join the major, you can sort of get into the real mathematical analysis of like what's the sort of average case. You do this amortized analysis stuff between the best case and the worst case and the like possible statistical probability of each one's. That's a real thing. There's this, I will say this thing called the in practice case. That's not a real thing. I made that up. But what I mean when I say that is we're going to get into some data structures where I can invent some really unlikely scenarios that will cause some really gross worst case scenario situations, kind of like that binary search tree that's just like one crappy linked list. That is technically a worst case scenario, but deeply unlikely to happen unless you specifically add values into that binary search tree in ascending or descending order, So like sometimes I'll be like, that's like it's technically a worst case, but like that's so unlikely to happen. Let's sort of talk about what the in practice case is. I think you could also use this term in industry and people would know what you mean. They're like, oh, like what is like within the realm of like statistical probability of how this thing would really behave in the real world. So you might hear me say some of those terms throughout course, but generally we're going to stick to the really clearly defined ones where I will ask about the asymptotic analysis or the case analysis in the best case, worst case scenario. Okay, how do I do case analysis? So one, we got to look at the code really closely, and we're going to ask ourselves how things can change based on the state of the input. Is there a state of input or like a search term or something that would cause me to say exit a loop early? Might I return from the method and like interrupt my algorithm before it ever finishes running? Those are things that would cause me to do a lot fewer instructions than if I let the loop continue all the way. So anytime you have like an if statement that has a return inside of it, or something that has an if statement around a break inside of a loop, those are moments where you could interrupt the possible number of iterations, base cases that could interrupt the flow of recursion. Those are things to think about in terms of like how could I interrupt the possible numbers of iterations or recursive calls or something like that that may happen. Then also think about what input values could cause you to do that, like not the number of inputs, but like in our example here, like 2 versus 8. We were looking at the same numbers of n, but one time I was looking for the thing that happened to be beginning, one thing I was looking for that didn't exist in the list. So what kind of values could trigger those branches that would interrupt the algorithm? Now here's the thing, is those may result in different code models, right? Like we saw they had different graphs, and I sort of showed you like one was like, f of n of 2. That means I found it and I bailed out. One was f of n of 3n plus 1. That was like I looped all the way to the end and then I returned false or something like that. So you could actually have 2 separate code models, and then from those code models you can apply asymptotic analysis. And this is another area that people tend to get very confused by, because people tend to mix up the worst case with the big O. But the worst case and the best case, those come before the asymptotic analysis, and you might have two different code models that represent the cases. So again, we're going to go back to our roadmap. We're going to start with the code. You might want to write the code model for the best case scenario and then the worst case scenario. And then once you've got the code models, you can talk about the upper and lower bounds or the theta of that code model. So for our 3n plus 1 situation, its asymptotic analysis, essentially, it's a linear complexity class, which means it has a big O of n, an omega of n, a theta of n. The best case scenario has its own big O, big omega, and big theta. They're just in the constant class. So big O is the upper bound of any code model. Worst case is something that may exist depending on the type of code you are. Some code will just kind of run the same no matter what happens. Like maybe it doesn't have a break in the middle of the loop or something. Like not every code has a differential between the best and worst case. But you will always, for every code model, have its own independent big O, big omega, and big theta style of analysis. Questions? Okay. I don't know if this helps. I stole this from another professor. But case analysis is just sort of like another dimension to compare your code against. And so here, this is our graphs we've been looking at. Like here's where n tends to infinity, and here's the function of the graph. And this is like the too fine position I'm looking at. So these graphs sort of lay on top of each other. It's just another dimension to analyze your code in. I don't want this to confuse you, but for some people, this makes a little more sense. Okay, let's pause for questions. I'm going to pop open the Slido, and let's see if there's any questions. Good question. Let's see. I'm confused about the tight upper and lower bound of a piece of code's runtime. Growth is always the same complexity class being false. Is there an example? It said it can't be. I threw a word can't in there, and I think I maybe double negative viewed on the intro. But the tight upper and the tight lower can absolutely be the same complexity class, and if they are, that's the big theta. If they are not, the theta does not exist. How do you differentiate simplified big O and simplified tight big O? Simplified, that's when I mean drop out the coefficients, drop out the constants. Tight means the thing that sits as close as possible. Like what's the closest bound? Because remember those definitions are sort of like pretty general. It's like big O is the set of equations, that upper bound. And so, for example, if I had a linear equation, the linear of big O is the tight, but technically n squared upper bounds it, technically n cubed upper bounds it, technically n factorial upper bounds it. But when I ask for tight, I mean the one that sits as close as possible. Yes, so the function is n. The tight, upper tight and upper lower would be n. That's true. I'm not sure. I probably had some like nasty double negative language, and I'm sorry if it confused you. Yes, see, this is a very, very, very common way to learn this at first, but remember, big O is applied to the function. The function can represent either the best case or the worst case. So you could have two different big O's, one for the best case scenario, one for the worst case scenario. That might be true. This one might be true where it's like, maybe there was like a couple, like instructions or something like that. And I'm sorry, I know we all want to be very specific about these numbers. I just don't care about like the specific numbers in a constant function. Maybe there's 2 instructions, maybe there's 3. You could probably convince me that it was 3. Cool. Any other questions that came up before we dive back in? Okay, I've done this in a minute of time. Maybe, yeah. Okay, cool. No worries. It's still percolating. Take it to the ed stem. All right, so now let's see how deep into recursive code I can get in 22 minutes. All right. So we've been writing these code modeling problems where we sort of apply one piece of instruction per basic code, and then we think about the control structures and all that good stuff. But if you have tried to apply that yet to a recursive piece of code, you've probably found that that model kind of breaks down. So we're going to talk about it. Here also, I like to talk about, there's some general patterns of recursive code, just in the nature of how these things are created. So one of the common recursive patterns that you will find is where we pass along the input to a recursive call, but we reduce the input down. So like, if we start with 100 items, we make a recursive call where we say half the input, half it down, and then our base case is when we only have one thing left to look at. For example, like binary search. Binary search in my head is like looking for something in the dictionary. If I give you a word to look up, it's alphabetically organized. Chances are you're going to open up to the middle of the dictionary. You're going to say, hey, is the thing I'm looking for before it? Then I don't have to look at anything after, so on and so forth. In fact, past Casey did a nice little animation for us. So, one, remember that binary search only works on sorted sets. If it's unsorted, this is a crapshoot. This algorithm does not work, okay? But if you have a sorted collection of things and I'm asking you to look for a value, let's say I'm looking for the value 42, I'm going to first look at the thing at the very perfect middle of my collection. And I'm going to kind of keep these three variables, min, mid, and max. And I'm going to say, hey, look, like that value in the middle, it's 30. 30 is less than 42. So it's like I can kind of just like eliminate everything that's mid or less, and then I kind of like shift my focus to only the top half. So in that one check, I've eliminated half of the things I might have to search through. And then I'm going to do it again. Like, what's the new mid? So that index 12 is the mid between 9 and 16. And I would say, oh, look, 56 is greater than 42. So I'm going to, again, eliminate half of the things I need to look at, and then I'm going to adjust again. And then, ooh, nice, 42 happens to be at my mid. So in this situation, I have found the thing I'm looking for with only having to do 3 checks. Very different from linear search, where I would just start at the beginning and move the way through. So this is what I call, when I talk about recursive patterns, I'm having the input, having the things I need to look at each time. Here is a bunch of really fancy math that I used to force you to write out that I'm not going to force you to write out anymore. That proves to you that this is what we now call logarithmic growth. That's why we get this graph that you can see sort of like starts fast and slows down over time. So it's actually kind of efficient as like we deal with it over larger things. So logarithmic time is, especially log-based 2 runtime, is when we're sort of eliminating the set of n I need to loop over or iterate on or process with every single recursive call. So now let's talk about case analysis in terms of binary search. If you were given a set of ordered values like I did there, remember our example with 42, the very first thing I'm going to look at is the very middle value, and then I'm going to cut in half and cut in half and cut in half. So where is the ideal spot for the thing I happen to be looking for so that I only do a single check? What is the best case? Yeah. In the middle, absolutely. So what if 42 had originally just been perfectly at the middle spot? Well, that's freaking convenient. Great. Then I just have one check, and I don't care how many other things are in the set. I have constant, and there is my constant asymptotic analysis. Flip side. What is the absolute worst possible situation for the thing I'm looking for? Yeah. Ooh, at the absolute most right or absolute most left, which is sort of the opposite of the middle. Yes, that absolutely counts because that will include the same number of checks. There's another one that will fall into the same exact runtime as that. Let's see here in the middle. Yeah, Washington sweatshirt. Yeah. Ooh, like right around the middle, same sort of idea, right? Like we know like those sort of extremes can be very hard for us to find. Yes, these things all take the same runtime. What's another possible value, like if I'm looking for it? Yeah. It's also not there. All of the things you just listed will take the same amount of checks. Just like if it's not there, that means I have to do the ultimate number of checks to determine the thing is not in the collection. Questions on that case analysis? Okay, great. So we're not found. That means we have to run the whole thing all the way through. It's logarithmic growth rate. So we get O, theta, and omega of log n. Yeah. So, cool. We did some case analysis, but I promised you that I was going to be doing the code model for recursive functions. So binary search is something we're a little more familiar with. It's a little bit easier for our brains to contextualize, but let's actually try to take this to the code analysis place. In the interest of time, here's sort of like the basics. So if you're looking at this piece of code, remember recursive code is sort of broken into the base case, which is definitely not recursive. The base case is where the recursion stops. That's like the test on your for loop. This is where the iteration ends. This is where the recursion ends. So the base case is always non-recursive. So if you're doing your code model, I like to start there. I'm like, oh, I don't know how to like model recursive code yet, so I'm going to model the non-recursive stuff. Then, depending on your piece of code, then there's the recursive case that happens if you didn't hit the base case. And even within the recursive case, there might be like some kind of amount of like non-recursive work that's hanging out in there. And if we look here, we've got, you know, this sort of recalculation of mid. We've got this sort of check here before we return. And this here is all the recursive case. And then we've even got this sort of check on the which recursive case to run. If I just talk about the code model for the base case here, here's actually an okay example where you can see, first we're going to check this if statement. So that's going to be +1. If it's true, I return. So there's a +1. But if this is not true, then I do need to do this check again. And then that means I need to do this check, which might be down here or down here. So when you have this type of branching structure, we know not all of these pluses are going to get executed, but if you can see, I'm almost always going to ask you for the worst case runtime. And so the worst case is if I check this if statement and that's false, then I check this if statement and that's true, and so then I check this if statement, and then technically those are sort of the same, but that's how I got 6 for the worst case of the base case. Then I go to the recursive case, and first again, I am putting off the hard stuff for later because that's the type of procrastinator that I am, and so I'm going to do the non-recursive stuff first. And so I see there's a bunch of numbers around there. The non-recursive stuff, that's there, it's like 6, and then we do some recursion, and like I haven't shown you how to represent that. So how do you model recursive calls in your code model? As it turns out, you literally use a recursively defined math function, enter the recurrence. Just because we love the same words. So I will say recurrence when I mean recursion and vice versa. I'm sure at some point, please forgive me. A recurrence is just a mathematical definition. Here's what it looks like. And so here we have T of n. That's the same thing as F of n. And then we have a branch up here. If you can't tell, this is the base case branch, essentially. And then we have a sort of case based on like when that triggers. And then you can see here within the recursive branch of this recurrence, you can see we have a reference to myself, t, and then I have entered in how the value of n changes. So remember, in binary search, I have n divided by 2. That's where that's coming from. And then some like extra recursion is happening here. I think this is maybe just an example. This isn't specifically binary search. But the 2 here before the t, that would mean maybe we're making 2 recursive calls. So we have some coefficient for the number of recursive calls. We have some call to myself, so t, and then we have some indication of how n will change between the recursive calls. And then we have those sort of cases. Great. Okay, let's practice. So let's see. Can we do this together? Yeah. Why don't you, I feel like I've been talking for a long time, why don't you take a few minutes, I've just given you all that stuff, try to write the code model for this, and you can see you're definitely going to want this type of T of n equals, and then that big old curly brace and the branches. You need that. Your top branch will be your code model for your base case. Your bottom branch will be your code model for the recursive case. You need to figure out for what values of n. That's what goes on the right-hand side there. But go ahead, talk about it, and then we'll come back together in 3 minutes. Go ahead, chat through it. All right, in the interest of time, let's talk through it a little bit. So we've got up here, we've got an if statement, return 3, and then we've got a for loop that runs over n times and prints something out, and then we've got some recursive calls. So maybe let's start with the base case. Does anybody have what they would consider to be the code model for just the base case? Yeah. 2. Yeah, I think that makes sense. Let's see what I said. Something like that. Yeah, 2. Looks good. Great. And you can see I did some of the other stuff in there, but whatever. Yeah, so that base case, and for what values of n is the base case going to be triggered? Less than 3. Absolutely. So in our recurrence, we've got our t of n equals, and then our big curly brace, and that top branch would probably say 2 when n is less than 3. And if it helps, look how identical that looks to the base case. It's like you can just count the basic instructions in the base case and then copy the if statement from the base case to that branch of the recurrence. Very common pattern. Not always the case, but a common pattern. Okay, so now then we've got the recursive case, which is everything else. And remember, there's always some non-recursive work. So we've got this for loop, we've got this return statement. Okay, great. Thanks, Casey. So here, what does anybody want to raise their hand and tell me, like, what's the runtime of this for loop? Yeah, way in the back. N. Absolutely. There we go. So we've got a factor of n going on. That's non-recursive work. We've got that return statement. So in my, like, non-recursive work, I've got n plus 2. Again, I'm a procrastinator. I've put off the hard stuff. So now it is time to talk about the recursive pieces. So the recursive pieces, how many recursive calls is this code going to make every time? How many recursive calls? 2. Yes, 2. So that will be our coefficient in front of the t. And then if we look in the parameter field there of the recursive calls, how is n changing? Yes, n over 3. So recursive work is 2 times t of n over 3, meaning 2 calls to the function where n is going to be reduced into a third each time. I'm just pretty directly translating. Coefficient, number of recursive calls, what's in between the parentheses of the t is just how n changes, which I literally just picked up and put in there. So here is the formal recurrence for this piece of code. Does anyone have any questions on how we got there? Yes, please. You're right. There should be a plus 2 on there. Absolutely. It should be, yeah, like plus n plus 2 is what that should say. You're absolutely right. Yes?
I'm wondering why we can just add the recursive part to the non-recursive part. Because like when we, like in the recurrence, the non-recursive part will also be implemented. So.
That is a fabulous question. It is answered on a slide that I really hope is the next slide. Is it? It's not the next slide. Gosh darn it. Okay, but I have a slide that is absolutely going to answer your question. Give me 2 more slides to get there. But excellent question. I'm going to put a pin in it really quickly. Okay, so let's assume for right now this is our recurrence, even though I missed that plus 2 off the end of it. Now you're like, Casey, why are we doing this? It is not any more obvious to get the big O out of this. Usually we have we just look at the function and we're like, what's the biggest term of n? Boom, there's my big O, right? Well, you could do some really fancy math that I used to force all of you to do, and my poor TAs to grade it. I did it for years, and I am now, congratulations, we've moved past that. We don't do that anymore. But if you want to know, what usually happens is you use a bunch of algebra to find what we call the closed form of the recurrence. It involves a bunch of summation identities. There's some terrifying slides in here from when we did that. If you're into that stuff, please feel free to take a look. But instead, we now use what we call master theorem. God bless a plug and chug. This is made by some fancy math folks that I don't know. And here you go. We have, as you can see here, a overall format of what your recurrence looks like. And you can see, you just figure out what these values are. So here, our D is 2, our A is 2, and then our f of n is n, and then our B is 3. I'm literally just like directly pulling those numbers based on what my recurrence looks like, and then I'm just plugging those numbers into these mathematical functions. And you can see if log base B of A is less than C, then it's n to the C. If it's log base B of A is C, then it's n to the C log n. Cool. And then if it's log base B of A is greater than C, then n to the log base B of A is your solution. So here is the plug and chug for our situation. I will let you practice with this. It's a fun time to plug and chug. The TAs will go over it with you in section, all that good stuff. If you want to know why it works, because I'm that kind of nerd, here's a bunch of explanations as to why it works. I used to get really excited and explain this to y'all, and then people told me it terrified them. And so now I'm just saying, on your own time, read about it. It's a good time. But it does make sense mathematically. You don't have to understand any of that piece of it. You just need to know how to pick which numbers are which. Great. Really quickly, damn it, the slide that I was looking for to answer your question is apparently way deeper in than I wanted to describe it to, but I promise you that you just get to add that recursive work or the non-recursive work off the end. Because we've got the definition of the function in itself, there is a slide in here about something called unrolling, and you'll see how that plays out. When you just actually plug the function into itself over and over, you start to accumulate these extra terms of the non-recursive work. So the definition still works because you're going to pick up a term of the non-recursive work every time you plug the definition into itself again. I'm sorry, I know that was really hand-wavy. I'll maybe put some like written description of that on the EdStem. Okay. This is apparently as far as I'm going to get today, so any questions? Yes?
On the last slide,
yes.
Where is the C in the master theorem in Q?
Oh my goodness, what an excellent question. You're right, it's not obvious, but it is the exponent of n. So, you're right, in our version it was essentially hidden here because if it's n, the coefficient is 1. If it's n squared, the C is 2. If it's n cubed, the C is 3. You're right. That's almost invisible. You would have theoretically gotten that from this tiny little sliver here, which everybody, I'm sure, visually missed. But C is the coefficient of the term of n in the non-recursive work. If you do not have a term of n, the C is 0. So if that didn't say plus n, it said like plus 2 or something like that, the coefficient of n is 0. Yes, question? Yes. Yes. So this f of n hanging off here is the non-recursive work within the recursive case. So the C is the coefficient of the term of n in the non-recursive work within the recursive case. If there is no non-recursive work, then C is 0. We will definitely revisit this on Monday. Don't worry so much. I will stick around and answer more questions if you have them. Have a fabulous weekend, everybody. See you on Monday.